The Physics of Interstellar Travel, Chapter 12, Interstellar Medium. To get to its target system, our spacecraft must first cross interstellar space. Although the particle density in the interstellar medium is low, it is high enough to be a hazard for a fast spacecraft, and we will need some kind of shielding. These particles also offer a potential means of propulsion in the form of the admittedly far-fetched idea of the Bussard ramjet. Before the spacecraft gets into interstellar space, it must first leave the solar system. What will it encounter along the way? The Sun emits a stream of charged particles into space. This so-called solar wind, which has a density of a few million protons per cubic meter, or a few per cubic centimeter if you prefer, reaches velocities of a few hundred kilometers per second. The density of this wind drops with distance from the Sun, and eventually the ram pressure it exerts equals that of the pressure exerted by the interstellar medium. The shell around the Sun where this occurs is called the heliopause, and it is sometimes taken as being the edge of the solar system. Voyager 1 crossed the heliopause in 2012, when it was about 120 astronomical units from the Sun. Out at this distance, there are still many planetesimals that are gravitationally bound to the Sun, not least the Kuiper belt and, further out, the Oort cloud. The Oort cloud, icy bodies believed to be the leftovers of planet formation, may extend as far as 50,000 astronomical units, a fifth of the way to Proxima Centauri, or maybe even more. We know very little about the Oort cloud, but it probably contains around 10 to the 12 kilometre-sized icy comet-like objects. These are spread over such a huge volume that the probability of our spacecraft hitting one on its way is completely negligible. We won't be doing any Hollywood-style asteroid dodging. Most of the mass of the ISM is in the form of individual atoms and ions, which we refer to as gas. This is 90% hydrogen by number, 70% by mass, followed by helium, with less than 0.1% by number in heavier elements. The density of the ISM varies by orders of magnitudes across the galaxy, but away from star-forming regions, it is typically around 1 particle per cubic centimetre. The closest region to the Sun, the interstellar cloud, has a density about 3 times lower. Dust particles have a much lower number density than the gas, with perhaps just 1 in every 5 million cubic metres, although this value is very uncertain. There are presumably larger particles, between, say, 1 millimetre and many metres, with an even lower density, but we have no observational data on these. Since 2017, we do know of at least 3 interstellar objects that are hundreds of metres to kilometres in size, similar to comets in our solar system, but their space density is too low to present any hazard to our spacecraft. As a spacecraft moves through the ISM at high speed, it will collide with many gas and dust particles. Because its velocity is much larger than the RMS velocities of the ISM particles, almost all of these impacts will be at the front of the spacecraft. ISM atoms will be completely ionized by their impact. The resulting high-energy ion interacts with the atoms in the spacecraft material, exciting or ejecting their electrons. The energy of the impacting ion is dissipated along tracks in the target material as it encounters successive atoms. This energy can cause local melting and so permanently damage the material. The distance over which the ion is stopped depends on its charge and velocity, as well as the density, atomic number, and ionization energy of the material. It is on the order of millimeters, but ranges over orders of magnitude. The electrons from the impacting atom have much less mass and so do much less damage in this way, but their deceleration produces significant amounts of X-rays through the process of Bremsstrahlung. These X-rays can heat and damage the spacecraft material too. Dust impacts are rarer, but because they are so much more massive, each impact causes more damage. Overall, simulations show that dust is a bigger hazard than gas for an interstellar spacecraft. It appears, though, that a surface layer of about 1 centimetre of graphite or quartz, for example, should protect the spacecraft from all but the largest dust impacts. Most of the area and much of the depth of the shield would be eroded by the time the spacecraft gets to Proxima Centauri. Very large dust grains would be almost impossible to shield against and could destroy the spacecraft. Such impacts are probably unlikely, however. One way to compensate for this is by sending a swarm of spacecraft, as we'll discuss in Chapter 16. Because most of the impacts come in the direction of travel, we will want to reduce the cross-sectional area of the spacecraft in that direction. Interstellar spacecraft will therefore be long and thin. Ideally, we would only deploy large structures, such as communication antenna or cells for braking, once the spacecraft is close to its destination. We learned in earlier chapters about the curse of the rocket equation. Rockets spend much of their fuel propelling the remaining fuel. One way to avoid taking propellant with you is to collect it as you go. Most of the ISM is hydrogen and could, in principle, be used to drive a fusion rocket. This is the idea of the Bussard ramjet. A large scoop collects hydrogen from the ISM, which is fused, and the high-energy products ejected out of the back. The spacecraft has to be moving to scoop up the hydrogen, so a ramjet only works once the spacecraft already has a small initial velocity. But after that, it will accelerate, and the faster it moves, the more matter it gathers, and so the more it accelerates, and so the process continues. Assuming that the hydrogen has to be stopped within the spacecraft for the fusion to occur, this will cause a drag on the spacecraft that will limit its velocity. If this drag could be overcome, and there are ideas for achieving this, then the spacecraft can keep accelerating, and in principle can eventually get arbitrarily close to the speed of light. Unsurprisingly, there are many unanswered problems with the Bussard ramjet. First, given the low density of the ISM, the collector has to be enormous, many kilometers across, to collect enough hydrogen, and yet it also has to be extremely light. Second, directly fusing hydrogen with hydrogen via the so-called PP chain is not only much harder than the process we looked at in the chapter on nuclear fusion, but is also incredibly slow, with a mean time between reactions of billions of years. We could instead use the CNO cycle to fuse hydrogen, which is a much faster reaction, but it needs a higher temperature as well as a carbon catalyst. Alternatively, we could use deuterium in the ISM, but this is about 100,000 times rarer than the lighter isotope of hydrogen, so our collector area would have to be 100,000 times larger. So while the ramjet is a nice conceptual idea, it is on the edge of being impossible. That brings us to the end of our brief survey of the interstellar medium. Although it is a highly rarefied medium, the ISM contains enough gas and dust that our high-speed spacecraft will suffer a large number of high-energy impacts during its journey. These can damage the spacecraft, although about 1 centimeter of massive shielding should be enough to protect the spacecraft against all but the largest dust particles. However, the size and mass distribution of dust in the ISM are poorly known, so this remains a significant risk factor for the first interstellar spacecraft.